For all the raw power they carry, supernovae remain one of the great unsolved riddles of science. We can point to the kinds of stars that are fated to tear themselves apart, yet we have no way of saying when the end will arrive. There is no countdown, no alarm, no date to circle on a calendar. Almost everything we understand about these colossal explosions has been pieced together not from the blast itself, but from the rubble it leaves behind, vast, glowing shells of scattered gas that we examine centuries, sometimes thousands of years after the light first flared. The only alternative has been luck. A telescope pointed at exactly the right sliver of sky at exactly the right instant. Not long ago, that long-standing pattern finally cracked. For the very first time, astronomers watched a star detonate as it happened, on purpose, by design, only hours after the explosion tore loose. It stands among the earliest glimpses we have ever captured of a dying star, and folded into that first faint light was a detail no one had ever measured directly. The shape of the explosion itself. A shape might seem like a small thing to marvel at, but the geometry of an exploding star is a kind of signature, and learning to read it could pry open a mystery that has defied physicists for lifetimes. How does the heart of a star collapse inward and then somehow erupt back outward? Why do some stars pull off that impossible reversal while others simply wink out of existence? What is the hidden trigger that turns an implosion into a flood of light? Armed with new data from a sky survey called ATLAS, we are inching toward those answers at last. So let's attempt something no earlier generation ever could. Let's watch a star die in real time, trace the shape of its wreckage as it forms, and look straight into the final, savage seconds of a giant coming apart. Because what happened in the spring of 2024 was not just another dot brightening in a distant galaxy. It was a rare, fleeting window, one that stayed open for only a handful of hours, into the exact machinery that drives the most violent events in the cosmos. And when that window closed, it left behind a puzzle even stranger than the one it was meant to solve. To understand why a single blurred smudge of light sent observatories on 3 continents scrambling in the dark, we have to start with the night the alarm first sounded. ATLAS. The Asteroid Terrestrial Impact Last Alert System was never built to hunt dying stars. Its job is to spot rocks on a collision course with Earth. To do that, it relies on 4 wide-field telescopes scattered across the globe, a pair in Hawaii, one in Chile, and one in South Africa. Working together, they sweep the entire visible sky roughly every 2 days, photographing each patch several times as they go. That relentless, rapid re-imaging is what lets the system catch things that flare up and fade fast. And in the small hours of April 11th, 2024, that is precisely what it did. At a single point in the darkness, a speck of light had begun to swell in brightness over the previous few hours, climbing far too quickly to be anything ordinary. The moment the software noticed, it fired off an automated alert, and word of the unexplained newcomer raced out across the global astronomy community. Telescopes and inboxes lit up. Somewhere in a spiral galaxy some 22 million light-years away, in a swirl of stars catalogued as NGC 3621, a massive sun had just reached the end of its life. What Atlas had stumbled onto was a Type II supernova caught almost at the instant of ignition. It would come to be called SN2024GGI. For one team of researchers in China, led by an astronomer named Yang, the discovery landed like a starting gun. Here, finally, was a chance to do something that had never been done, to measure the true, unspoiled shape of a supernova explosion while it was still unfolding. But the clock was already against them. A supernova is not only impossible to schedule, its opening act is heartbreakingly brief. In those first hours, the blast still wears its original form. After that, the outrushing debris slams into the gas and dust wrapped around the star, twisting and smearing the shape until every trace of the pristine geometry is lost. The one clue capable of revealing how a massive star truly dies would survive for only a moment. To catch it, they would have to move faster than they ever had. There would be no second attempt. Whatever the explosion looked like in its earliest breath, it would have to be recorded now, tonight, or not at all. To grasp what makes that shape so precious, we have to descend into the star itself, into the moment everything gives way. Across their enormous lives, massive stars survive by fusing light elements into heavier ones, welding atomic nuclei together in their cores. Each fusion step pours out energy, and that energy pushes outward, holding the crushing weight of the star's own gravity at bay. It is a standoff that can last millions of years, hydrogen fusing into helium, helium into carbon, then oxygen, neon, silicon, each stage burning faster than the last as the core climbs the periodic table. Then it reaches iron, and iron is where the ladder ends. Iron sits at the very bottom of the nuclear energy well. Its nuclei are bound more tightly than anything else. Fusing iron into something heavier doesn't release energy, it demands it. So when a star's core finally turns to iron, the fires go out. The outward push that held everything together for eons simply stops. What follows is almost too fast to picture. With nothing left to resist it, gravity wins instantly. The core caves in on itself, the outer layers plunging inward at speeds approaching a quarter of the speed of light. The collapse is so ferocious that it crushes protons and electrons together into neutrons, forging an ultra-dense neutron core at the center, and unleashing a torrent of neutrinos, ghostly particles that stream outward, carrying away staggering amounts of energy. Then comes the rebound. Infalling matter smashes into that newborn neutron core, which is too stiff to compress any further, and slams back outward as a shockwave, a burst of energy racing out at thousands of kilometers per second. This is the moment a star is supposed to explode. But the shock doesn't get far. Within a heartbeat, it grinds to a halt somewhere between 100 and 200 kilometers from the center, choked as it tries to plow through the dense iron still raining down. The heat shatters that iron back into lighter particles, a process that drains the shock of its energy. And here, everything hangs in the balance. If the shock stays stalled, the star keeps swallowing its own falling matter until it collapses into a black hole. No flash, no glory, just silence. A failed supernova. But if something revives that dying shock, neutrinos, jets, magnetic fields, or some tangle of all three we haven't pinned down, the implosion flips into an explosion. Exactly how that revival happens is one of the largest open questions in all of astrophysics, and it is the reason a star like SN 2024 GGI is worth chasing through the night. If the shock does come back to life, it begins a long climb outward, grinding through thousands of kilometers of stellar gas over the course of several hours. Finally, it reaches the surface and bursts through, and the star lets out a brilliant flare of ultraviolet and visible light, its outer skin flashing to tens of thousands of degrees. This is the breakout, the first instant the explosion becomes visible to us. The star begins to brighten and will keep climbing toward its peak over the following week or two. That opening surge of light is exactly what Atlas registered in the dark of that April morning. But spotting the flash was only the opening move. To capture the shape, Yang's team needed something far rarer than a routine image. They needed to fight their way onto one of the most capable instruments on the planet, the Very Large Telescope in Chile. And They needed it immediately. Through the night, they hammered out an urgent request to the European Southern Observatory, and to their relief, it was approved. The Great Telescope turned toward NGC 3621, and the data began to flow with barely any margin to spare. Bolted to that telescope is an instrument called FORS-2, the only one of its kind in the southern sky. Its specialty is spectropolarimetry, measuring how the light coming from an object is polarized across every color of the spectrum. And polarization, it turns out, is the key that unlocks shape. Most light vibrates in every direction at once. That's ordinary, unpolarized light. But when light bounces off a surface or scatters through an expanding cloud of debris, it can end up vibrating mostly along one plane. That's polarized light, the same effect that polarized sunglasses are built to cancel when they strip the glare off water or glass. Here is why that matters for a supernova. A perfectly round explosion scatters its light evenly in all directions, and the polarization from every angle cancels out to nothing. But a lopsided explosion, one stretched along an axis like an egg or a football, leaves a distinctive polarized imprint that betrays its true form. FORS-2 reads that imprint by passing the incoming light through a rotating crystal plate, and then a Wollaston prism, which splits the beam in two according to how it vibrates. Comparing those two split spectra, color by color, reveals both how strongly the light is polarized and in which direction, and from that, the shape of the blast. For roughly 50 years, theorists have wrestled with a single question: what breathes life back into that stalled shock and lets a star explode at all? Out of decades of argument, two leading pictures have emerged. The first says, neutrinos do the work. The collapse floods the region above the neutron core with those ghostly particles, and in the crushing density just overhead, a small fraction of them finally snag, dumping their energy into the surrounding gas and heating it from below. That heat stirs up violent churning and convection, and if enough of it builds, the shock roars back to life and the star blows itself apart. Cutting-edge three-dimensional simulations, including work led by Bernhard Müller and his colleagues at Monash University, show that this kind of blast comes out messy and lopsided, riddled with turbulent blobs. And we see hints of that in real wreckage. The famous remnant Cassiopeia A is streaked with uneven pockets of radioactive elements like titanium and nickel, scars of an explosion that was crooked from the very start. The second picture says jets are the culprit. In this version, the collapsing core spins up into a rapidly rotating neutron star, wrapped in a disk of infalling matter. Magnetic fields threading that disk get wound tighter and tighter by the rotation, coiling like an overstretched spring, until they funnel material into two powerful beams that blast outward along the star's spin axis. Those jets drive a very different kind of explosion. One stretched and elongated along a single axis, giving the blast a football-shaped, or more precisely, a prolate geometry. And we've caught that elongated, orderly structure in other supernovae we studied long after the fact. So, which was it for SN2024GGI? A ragged, chaotic mess, the calling card of neutrinos, or a smooth, stretched football, the mark of jets? When the polarized light from FORS-2 was finally decoded, the answer looked stunningly clear. The explosion had a well-defined axis of symmetry and an elongated, football-like form, a prolate shape, exactly the kind the jet model predicts. Had neutrinos been running the show, the blast should have come out lopsided and irregular. Instead, it was strikingly organized. For a moment, it seemed like a decisive victory for the jets. The mystery, at long last, appeared to be solved. Except nature is rarely that tidy. The neutrino picture has a stubborn flaw. When researchers run it in full 3 dimensions, the explosions that come out are far too feeble. A study back in 2015 found the simulated blasts falling short of real supernovae by around a factor of 10. Neutrino heating on its own, it seems, just can't summon enough force. But the jet picture stumbles too. In 2 dimensions, the jets behave beautifully. Push the same setup into 3 dimensions, though, and something breaks. A team at Caltech nudged the spin axis of a rapidly rotating, magnetized core by a mere 1%, and that whisper of imperfection wrecked everything. The jets went unstable, writhing and coiling around the rotation axis, thrashing like a loose garden hose with the water still on. Instead of drilling a clean channel out through the star, they smeared into 2 twisted, tangled lobes that oozed outward and stalled. No explosion ever came, and yet SN 2024 GGI plainly did explode. So something in the story is still missing. The way out may be to turn the old idea inside out. What if that fatal wobbling isn't a flaw in the jet model, but the very heart of it? If the jets thrash and jitter too wildly to bore a clean tunnel, they're forced to unload their energy close in, roughly 1,000 kilometers from the center, hammering the surrounding gas with shocks. Those shocks inflate scorching bubbles of pressure that swell and merge, shoving the star's outer layers outward and finally driving the blast. The jets themselves stay chaotic, but the explosion they leave behind comes out smooth and symmetric, exactly like the shape we measured in SN 2024 GGI. So where does that leave us? SN 2024 GGI proved that these explosions can carry a clean, organized axis of symmetry. But how that order arises through jittering jets, through some magnetic rotational engine, or through something we haven't yet imagined is still unknown. We can't even say for sure what role, if any, neutrinos play. And we're left with fresh questions about the lopsided remnants like Cassiopeia A that refuse to line up along any axis at all. The honest answer is that one explosion isn't enough. SN 2024 GI is the only breakout we've ever measured in this kind of detail, this early. To find the pattern, we need dozens more. And for the first time, that finally feels within reach. A new wave of sky surveys is coming online, from the Vera C. Rubin Observatory, which began its landmark survey in 2025, to NASA's SPHERE-X mission and the latest data from the long-running Sloan Digital Sky Survey. Astronomers now expect to catch supernovae within 24 hours of ignition, whipping powerful instruments onto them before their shapes are lost. Each one we capture will chip a little more off the mystery of how the largest stars in the universe meet their end. Somewhere out there, another star is already counting toward its last second. Subscribe and be watching when the sky lights up.